What's good? Welcome back to my channel, Quantum Penguino. Today we're going to be discussing Noether's theorem, which states that continuous transformations on the action of a physical system result in a conserved quantity. This conserved quantity is the current, which is shown here on the title slide. As always, we start with some formalism, which is that we consider a continuous transformation on the field phi, such that it becomes offset by some infinitesimal parameter alpha and some deformation of the field delta phi. The transformation is considered a symmetry if the action or Lagrangian remain invariant up to a surface term. The reason they can remain invariant up to a surface term is that when we're deriving the Euler-Lagrange equations of motion, these surface terms end up integrating to zero. So this part is going to look really familiar if you saw my Euler-Lagrange video, but we're basically just going to take the Lagrangian and apply this deformation to the field, and then take a first order Taylor expansion to get the expression below. Then we realize that the second term from our expansion, after the two Lagrangian terms cancel out, can be expressed as a product rule. So we can algebraically manipulate our expression by substituting back in the other part of the product rule. After substituting back in this product rule expression, we can group terms that have a delta phi together and realize that these two cancel out by the Euler-Lagrange equation, and then we're left with our final result. So if we remember from the formalism given in Peskin and Schroeder, this current, which is the difference in the Lagrangian, should be equal to this J mu. At first glance, they seem like they should just be equal, but it's not quite the case because they're both derivatives. So since they can have some constant term that we're not accounting for, it's the derivative of their difference that's equal. They're not directly equal. But from here we get a result that is described by Noether's theorem. We have this little J mu, which is the argument inside the derivative, and we can say that this Noether current is conserved when the divergence is zero. And a small note I want to make is that this J mu represents any additional surface term that can be added that keeps the action in Lagrangian invariant. However, it's totally fine if this J mu is zero. So first we can start with a very simple example of a Lagrangian that's purely kinetic and transform the field by some small factor alpha. We first want to show that the Lagrangian is invariant under this transformation, so we just displace the Lagrangian by this factor of alpha and realize that the partial derivative cancels out the constant alpha and just leaves us with our original Lagrangian. Then we want to derive the Euler-Lagrange equations of motion, which is also pretty straightforward. The Lagrangian is only a function of the divergence of phi, so the second term cancels out, and we can just take a simple derivative to find the first term and get our equation of motion. So now we want to see whether or not the Noether current is conserved. We take the same approach as we did when deriving the equations of motion and take the derivative of the Lagrangian with respect to the divergence of phi, and we see that through a pretty straightforward derivative we arrive at our equations of motion being equal to the divergence of the current. So we can just easily say that it's equal to zero and that the current is conserved. So that was a pretty straightforward example, and we can now move on to something a little bit more complicated. Here we're going to have a complex field, and what we're going to show is the global U1 phase symmetry has a conserved current. By global U1 phase symmetry, I mean that this phi being transformed by this factor of e to the I alpha is a transformation along U1. So to show that the Lagrangian is completely invariant, we have to expand these magnitude squares for each of the phi and its divergence. And what this basically does is just pops out an extra factor of the complex conjugate of the argument. We realize that these factors of e to the plus or minus I alpha are constants that can be taken out of the expressions and canceled out with one another to just leave our original Lagrangian. Next, we use the Euler-Lagrange equation to find the equations of motion, but note that we split this into a real and complex part for the real and complex part of the field. So finding the real part of the equation of motion first, we expand the magnitude squared terms in the Lagrangian, again to be multiplied by their complex conjugates, and take derivatives. The only thing here that's not exactly straightforward is that when you're deriving with respect to an operator that has a lowered index and your term has an upper index, you have to be careful to include a factor of the metric tensor to account for the difference in sign between the two upper and lower indiced operators. Otherwise, we can simply derive and notice that these two crossed out terms go to zero as they're being derived with respect to terms that are just simply not in them, and we're left with our equation of motion for the real part of the field. Now we derive the complex part of the equations of motion. It's the same procedure except we now derive with respect to the complex field, and we get a very similar result to what we did for the real equations of motion, except that it's the complex conjugate. So now we want to show whether or not the current is conserved. This part is going to be a bit algebraically intensive, so I'm going to try to take it a bit slower. First, we're going to assume that this infinitesimal parameter alpha is a lot smaller than 1, so we can use the small angle approximation on e to the I alpha and the trigonometric terms that compose it to get these expressions of 1 plus I alpha and 1 minus I alpha for delta phi and delta phi star respectively. We have our equation for the conserved current, and we realize that there's now two terms, one for real delta phi and one for complex delta phi, and we can plug in our expressions for e to the plus or minus I alpha in for both of them respectively. Now we're going to take the derivative of the Lagrangian with respect to real and complex phi. Note that these are the same derivatives that we were just taking when deriving the equations of motion using the Euler-Lagrange equation. Now things are going to get a little bit messy. We apply the divergence that's outside of the expression onto the two terms that are within the parentheses and apply product rule to both of these. Now we can be a little bit clever and realize that these two terms look eerily similar to what we have in our equations of motion shown on the bottom line. So what we can do is we can substitute in these products of divergences for the mass terms in the respective equations of motion. These two mass terms that we just introduced cancel each other out and we're left with the equation on the bottom. Although these terms look different, they actually are exactly the same. This is because the order in which you multiply an upper versus lower index divergence doesn't really matter, because in the end, your space-time coordinates will all get the negative sign attached to them. So everything cancels out and we confirm Noether's theorem and don't break physics by showing that the current is conserved. So those are the two main computationally intensive examples I wanted to cover, and I want to briefly mention this example given in Peskin and Schroeder regarding what happens when we do a space-time translation on x mu such that the coordinates x mu go to x mu minus a mu through an infinitesimal translation. You guys may be noticing a pattern, but what we're going to first do is take a first-order Taylor expansion on both the field and the Lagrangian. The Taylor expansion of our field is pretty straightforward. We just get this alpha mu times the first-order divergence of our field. However, we notice something a bit unique for our Lagrangian. When we take this first-order Taylor expansion, we actually get a surface term that comes out. Now this is a bit different from the previous two examples that had that j mu both being 0, but in this case of a space-time translation, we do have a surface term that we need to account for. Now this term won't affect our derivation of the Euler-Lagrange equations of motion, as when we integrate over a surface term, it just goes to 0. However, it's important to be aware of this term as it's necessary to conserve the Noether current. Then when we write out the Noether current, we take delta phi from the deformation of the field, and then we take the j mu from this first order term that pops out of the Lagrangian. So now we have our first case of a Noether current having a non-zero surface term, and then this closed form for the Noether current is actually called the stress energy tensor, which helps us model the distribution of energy, momentum, and stress in 4D space-time. So thank you everyone for watching. I hope you enjoyed. If you have any feedback or I did something wrong, please say so in the comments, and yeah, see you guys next time.